in case you didn't look at it, the quiz was basically walking through talking about area in the 3 different ways that Chattery pointed out we talk about area in calculus. So the first way that I put down was really just geometry. So the first 2 questions should not have involved calculus. They're really just looking at the geometry of this thing. So the function that I gave was y equals x plus 1. And we were looking on this for x being between 2 and 5. And this is just something that I wanted to point out. A couple of you wrote the problem down wrong. So either wrote the wrong function when you copied it onto your paper, or wrote the wrong interval when you copied it down onto your paper. So just getting ready for that, for your first test on Wednesday, just be really sure that as you're moving the problems, like from the PDF onto your own handwritten work, just make sure that you're copying the problems down as they are written. Okay, so the first part of the question number 1 was to just sketch this. So problem number 1, this right here is a line. It has a slope of 1 and an intercept of 1. So it's going to look something like this. And then in terms of the interval, we were going from 2 to 5. And we could go ahead and label those heights right now. So when x equals 2, that means I'm at a height of 3. And when x equals 5, when we plug in 5 here, that means I'm at a height of 6. The second question on the quiz, I think I confused people because I think some of you were trying to use calculus and to use a trapezoid formula as a part of summation. But number 2 was just straight up use geometry to find the area. So no calculus involved. We should just be using geometry. And I gave you the formula because I wasn't sure if everybody remembered it. So one formula for the area of the trapezoid looks like 1/2 times the base times height 1 plus height 2. So looking at our picture here for the trapezoid we're talking about, the base of that trapezoid is 3. And I've already labeled my 2 heights. So I've got a height of 3 and a height of 6. And you could have left it at that, or you could multiply that out and it works out to be 21/2. So that part of it, no calculus. Then moving on to question 3, now we're getting into the calculus part. But before I keep going, because apparently I can't do math, three, 6. I think I maybe can't do math today. 3 plus 6 looks like 9. 9 times 3 is 27, not 21. How am I doing? Better? 27 over 2. You know, mathing it. Okay. Now moving on. There is another question in there about printing out the test. Absolutely, you can print out the test and write on the test, but not everybody has a printer at home. So I'm imagining some people are going to be copying problems down. Okay, back to my quiz. So question 3, now we're getting into the calculus stuff. And this is where some people wrote down the formulas for each of the parts for question 3. But the idea was actually to apply the formulas for this particular problem. So when we look at like 3A, for example, and there was A, B, C, D, but the first part was, what's the width of each rectangle? Well, for part 3, for question 3, what I've said is we're going to use n rectangles and right-hand endpoints. Since we're using n rectangles, the width of each rectangle we're just going to write it as that our delta x, we're going to take it from b minus a over n to actually plugging in the 5 minus 2 over n, so that we're looking at 3 over n. For that, okay, so I'm not going to ignore the questions in the chat. I'm going to finish this problem, and then I'm going to come back to address the questions in the chat here. So for the second one, on the ith rectangle, the x value will be x sub I. So that x sub I formula looks like a plus I delta x, but we're going to apply that to our actual function. So this is going to look like 2 plus 3I over n. For the next one, right, we had an A, a B, a C. For part C, I'm just asking you what the y value or the height is. So we're going to take that we're going to take that x sub I that we have and plug it into our function. So our f of x sub I should look like 2 plus 3I over n plus 1, because this whole thing is really my x. And some people simplify this, which is fine, to call it 3 plus 3I over n. Totally fine to do that. Part D, we're putting it all together into our Riemann sum notation. And in particular, I've already prompted us with the limit as n approaches infinity and the sum from I equals 1 to n. So now we just have to fill in the base and the height. But we're going to use the base and the height that we just figured out in the problem. So my base is over here, 3 over n. I'm just going to erase it because I'm running out of room. So my base is that 3 over n. And the height is this thing that we just found. And you could leave it in its unsimplified form, or you could add the 2 and the 1 together and put that as 3 plus 3I over n. And then the last question on my quiz, question 4, is our newest notation for putting this together. And that is, if I want to represent this area as a definite integral, then that definite integral, the height function, is just the x plus 1. It's the function that we have for our graph. And then our base, or our delta x, when we're putting it in definite integral form, becomes dx. And my limits of integration say I'm going to take those rectangles as far to the left as 2 and as far to the right as 5. So this would look like 2 to 5. And that's all you needed to do. You didn't have to actually evaluate that, though for practice, we definitely could. So there is a question back here on part C, and that's, where the heck did that 1 come from? So part C says we're going to take the answer that we got for the x sub I and plug it into the function. Again, because the idea for both 3 and 4 wasn't just to have you write down the generic formulas, but to actually practice taking a function and applying the formulas for it. So I'm going to take that x that we just found, plug it into the function, and that's where that plus 1 came from. And then for part D is, I'm going to erase that because I think maybe visually it's getting cluttered. But for part D, we're just plugging in the base, which is delta x, and the height, which is our f of x sub I. So if you didn't have a chance to finish all of these, that's okay. But I will say that you want to be working on speed a little bit, because speed's going to be important given that you only have 24 minutes to finish the test. So let me, okay, so here we go. If I'm finding the antiderivative, I'm going to use that basic rule. This thing's a polynomial, so I'm going to add 1 to the exponent and divide by the new exponent. And I'm going to do a little bit of the math in my head here. So 3x squared is going to become 3x cubed, but when we divide by 3, the 3's will cancel, and I've got x cubed. On this next one, my new exponent is going to be x to the 5th, but when I divide 10 by 5, I'll have 2. And that negative 12 is going to become a negative 12x. And then because I want to get all my points on the test, I'm going to write plus c. On this next one, anytime we have an exponential, I'm going to keep that exponential the same. So this is going to look like y equals 4e to the negative 3t, but I'm going to divide by negative 3 because I have that constant times my exponent. Again, I want all my points. Here's a plus c. On the bottom one, I'm going to pay attention that it told me that t is my variable. So when I integrate 5, or when I find the antiderivative of 5, that's going to become 5t. Now I need to know whose derivative is equal to positive sine. And that's going to end up being negative cosine plus c. If we take this one step further, right, because kind of 2 things for 4.6. One was finding our general antiderivatives, and then the other was solving something with an initial condition. I'm going to erase these and write another problem. So there is a request to do one with fractions. Heck yeah, we would do with fractions. I'll make my next one have fractions. And I'm even going to make it have gross fractions. And what I mean by gross fractions is that, let's say on this next one that, so here, instead of finding the general antiderivative, we are going to find the particular solution. And the function that I'm going to give us here, or rather the derivative I'm going to give us, I'm going to say dr dt is equal to, and I don't know what kind of fractions people wanted, but you're going to get my kind of fractions. So let's say we've got 4t cubed minus t squared all over 7t to the 5th. Sure. And if we're going to find the antiderivative here, right, or rather the particular solution, first step, I got to find the antiderivative. Next step, I'm going to plug in some sort of initial condition, which means I need to give us one more piece of information. And let's say that that piece of information that I give us is that r of 1 is equal to 5. And this might work out really messy, and I don't care. We're just going to go for it. First step is to find the antiderivative, but I'm going to back up and do one extra step first. And that is, when I am looking at this in the 4.6 context, I'm hoping that I can make this look like a number times x raised to a number. But to do that, I have to deal with the fraction first. This, I'm not doing calculus yet. I'm going to start by doing a little bit of algebra and say, this is the same as 4t cubed over 7t to the 5th minus t squared over 7t to the 5th. So I'm going to write this as 2 separate fractions. On that first fraction, I know that I'm going to end up with 4 over 7 for like the number part. And then for the t's, I'm going to subtract the exponents because we've got division. So t cubed minus t to the fifth, I'm going to end up with t to the negative 2. Here, there's an invisible 1 on top. So when I rewrite this, I want to make sure that I write this as 1/7. Now with my t's, I've got t squared on top, t to the fifth on the bottom, which is going to make that 2 minus 5 is going to give me a negative 3. Plus, oh wait, we didn't take an antiderivative yet. I don't know what I'm doing. Here, all we did was the algebra part. Now we're ready for the calc. For my antiderivative, we're going to add 1 to the exponent, divide by the new exponent. Well, when I add 1 to negative 2, I get negative 1. And dividing by negative 1 is really the same thing as just writing this as 4 over negative 7. On this one, I've got that negative 1/7. When I add 1 to the exponent here, that'd be a negative 2. And then I'm going to divide by negative 2. Dividing by negative 2 will turn this into a positive and turn my 7 into a 14. Since we were finding the antiderivative, I'm going to remember to put in the plus c. For our next step, we're going to work with this initial condition. And I've given us kind of ugly numbers, but the point that I want to make is we really don't have to simplify on this next step, not in the context of a test. So this step says I'm going to plug in 1 for t, and I'm going to set r equal to 5. And if I do those two things, I'm going to have 5 is equal to, well, my choice of 1 makes life convenient because 1 raised to any exponent is still 1. So this will become negative 4/7, and this will just become plus 1/14 plus c. And especially if you were running out of time, we're like running out of time on stuff, then we can definitely just move everything over to the left-hand side and make this 5 plus 4/7 minus 1/14. And that is my advice for a test, is not to mess around with finding a common denominator on fractions. Just roll with it. That whole thing is c, which means my final answer would look like negative 4/7 t to the negative 1 plus 1/14 t to the negative 2 plus 5 plus 4/7 minus 1/14, and walk away. If we were taking a derivative and we have a fraction, we kind of have two options in 17a, right? We could have done, just thinking generally, I could write this, if I was trying to take the derivative of that, I could think about it as a quotient rule, the way it's currently written, or I could multiply this over and then think about it as a product rule. So if we kind of think along those same lines of bringing this up, then the other way that we could rewrite it, instead of immediately going to it as the two separate fractions like I did, we can bring that 7t to the 5th up and multiply it out. And for some folks, that's definitely going to feel more natural, right, to do that. And then the thing that we want to be super careful about is if I'm going to like move that 7t to the 5th up, that 7 does not have an exponent. So I'd really have to think about this as 1/7 still, making sure that that 7 stays in the denominator, and then t to the negative 5th. And you could absolutely bring that up and then distribute it out. And if we distributed this out, then we should end up with the same thing, the 4/7, and then t cubed times t to the -5th. Now I'd be adding those exponents, so I'd still get the -2. When I distribute this here, I'd have the -1/7. And again, now that we're multiplying, we'd be adding those exponents and get t to the -3. The thing that we can't do is to just separately take the antiderivative of the top and the antiderivative of the bottom. And just like we couldn't do that when we were talking about product or quotient rule, we can't do that when we're trying to find antiderivatives. So the question about like the relationship between the exponent and the coefficient. So correct, the exponent and the coefficient are like separate things unless they're in parentheses. And I don't know if I've said this before, but I am completely convinced that most people have a separate fraction brain. And when you see fractions, other parts of math turn off in your brain because it's a fraction, but all that math still works the same. Just like if I had 3x squared, this isn't telling me that the 3 is squared. It would have to be in parentheses for it to mean that the 3 was squared. So that exponent of 5 only applies to the t, not to the 7, which is why that 7 really has to stay in the denominator, even when we pull the t up. I think it would be weird, but not mathematically wrong, if you really wanted to think about sort of pulling the 7 up to the numerator the same way that we did the t, you'd have to write that as t to the -1. I just think that that makes it more complicated, not less complicated. Chidori specifically said in lecture that he would not ask you to do midpoint. So I'm not going to do midpoint. You might be asked to do left-hand endpoints or right-hand endpoints if we have a finite number of rectangles, finite being meaning like a specific number. So here we have a specific number of 3. So let's practice both left-hand endpoints and right-hand endpoints. For our left-hand estimate, I've got my chunk from 1 to 4, and I have to break that up into 3 pieces. So that total, 4 minus 1, and then divided by 3 is what's giving me my delta x of 1. When we do left-hand endpoints, we're going to have our delta x, which in this case was 1. And then I know that because I have 3 rectangles, I'm going to have 3 things that are being added up. And the only thing that we really have to figure out is what x values we're plugging in. So when we do left-hand endpoints, I'm going to start on with my left value and go 1, 2, 3. 1, 2, 3. So my actual sum here, I'm going to plug 1 into my function, so I'll have e to the 2, plus when I plug 2 in, I'll have e to the 4, plus when I plug 3 in, I'll have e to the 6. And if this were the test on Wednesday, I would stop there because I'm not going to reach for a calculator. I'm ready to put it into a calculator, and that's where we want to get the problem to. So that's my answer. If we do right-hand endpoints, now, same deal, I need my delta x. And what goes in here, because it's 3 rectangles, I still need 3 of these. But my heights are going to come from starting on the right-hand side this time. So I'm going to have a 4, a 3, and a 2. So when I put those in, f of 2, f of 3, f of 4. And I'm going to have 1 times when I plug in 2, got e to the 4th. When I plug in 3, 2 times 3, I get 6, e to the 6th. And when I plug in 4, 2 times 4 is 8. I've got e to the 8th. Now it could ask us for each of these whether it was an overestimate or an underestimate. And here, this is where a picture really helps me. So when we draw in our left-hand endpoints for this particular function, those left-hand endpoints are all under the curve. So our left-hand estimate is the lower estimate or an underestimate. For the right-hand endpoints, all of those rectangles would all be above the curve. So this is my overestimate. But what if I didn't give us a specific number of rectangles and I actually wanted to express the area as the limit of a Riemann sum? Oh, the question about, do you have to add the right-hand endpoints? If you have gotten to this part, you should walk away. You have 24 minutes to do this test. Go focus on another problem. And specifically here, we can't do any better than that without a calculator. So we're definitely just going to walk away. You do have to get it here, not here. You should have actually plugged in the x values before you stop. Okay. So what if we reverse this or rewind this a little bit and say, I don't want an overestimate or an underestimate. I don't want to estimate it at all. I want to find the true actual area. So 5.1 is not antiderivatives, sorry, but 5.1 style, if I want to find the actual area, I'm going to express the area as the limit of a Riemann sum. I'm going to erase these. And the first part is always the same, no matter what our problem is, because we know that we've been told we should always use right-hand endpoints if we're having to do it as a limit. So we're going to go the limit as n approaches infinity, the sum from I equals 1 to n. That's the part we get for free. Next, I need delta x, and I need f of x sub I. And these two things are both going to be particular to our question. So here, to get my delta x, I'm going to have 4 minus 1 over n. We're going to leave it as an n because we're taking the limit of the Riemann sum. Limit as n approaches infinity, sum equals 1 to n, 3 over n. Now the next part for the f of x sub I always do that in two pieces. So I find my x sub I first, and the formula for that is a plus I delta x. So in this case, it'll be 1 plus I times 3 over n. And then I take that and plug it into the function. So this is going to look like e to the 2 times all of that stuff over there. That's our x value. 1 plus 3i over n. And then we stop because we actually don't know how to evaluate this limit. So we stop and we walk away. Oh, question about would it give us the interval? Absolutely, you'll be given the interval. So it'll either be given to you written as like x, it'll either be given to you like in interval notation, or written out like that, or for x between 1 and 4. Right, so a couple of different ways that you could be given the interval, but you'll be given the interval. When you get here, stop. If it's really bothering you, you are totally welcome to distribute that 2 in, but there's nothing else we're going to be able to do to it. So my advice is just stop. Again, we're not talking about this in the context of rectangles, just talking about this in the context of sigma notation for the test. So I'm going to break this apart because that's one of our sigma notation rules. So I'm going to write this as the sum of 3 minus the sum of 4i. And both of these are going from I equals 1 to 9 in this particular case. Now I'm going to apply that sigma notation rule that says when I evaluate this, I have 9 sets of 3, or I get 3 times 9. And then over here, that 4, another one of our sigma notation rules is that I can move the 4 out front so that this becomes 4 times the sum of I from 1 to n. And that's one where we're going to have a formula. And I'm 95% sure if you need it, it will be given to you on the test. But you could also put it on the formula sheet. And that formula looks like n, meaning whatever number is on the top, times n plus 1, all over 2. And then if this were the test, I would stop here. You have the answer in a form where it is ready to be plugged into a calculator. If it bothers you to not simplify it, then simplify it. Otherwise, I would just walk away. So there are tons of questions. Questions that are popping up are, one of the questions was, do we cover everything in 5.1 that he said would be on the test? Those are all the things in 5.1 that he said would be on the test. He did say that we need to know, how did he frame it? Basics of sigma notation. To me, this is basics of sigma notation. So I think it is possible that something like this would be on the test. We've seen it on the web work homework, so it's definitely fair game. And this is what I would call the basics of sigma notation.